Hello and welcome to the 8th part of a series of videos aimed at developing retro games in vanilla JavaScript using the canvas element. My name is Anthony, and please join me in my corner of the web where I like to build stuff in the browser with the latest technologies. We've not looked into either the background or the stage code since the second part of the video series, although since then we've been using a static image we borrowed from a Street Fighter fan site. This was good enough to get us where we are today, but if we're looking to replicate how the original game looked or behaved, we're missing a number of features at the moment. Now that our fighters are in a more comfortable place, I think we should look to rectify that a little in today's video. So let's jump right in and have a look at what we'll be attempting to complete in this video. We'll again bring up the ready to do list once more, and see where we are on the list of things we potentially have to complete. Scrolling through the list, there's a number of items that relate to both the background and the status bar overlay, which we can look to complete today. So in summary, in this video, we'll look to build the infamous overlay at the top of the screen. This will include the health bars, the battle timer, and the current associated fighters' name tags. I'll then move on to replacing our current background with the actual stage layers, initially replicating what we have now with the static background, before opening the boundaries to enable scrolling to the complete stage. To do this, we'll look to understand how to add a camera type system, which will also lead us on to understanding parallax scrolling, and how to handle the layers required to build Ken's background. Then finally, we'll get the fighters to interact with the camera and enable it to follow them around. And before we jump into the video, I'd like to quickly talk about the Patreon page I've set up, which I touched on in the recent vlog. Honestly, I'm still playing around with the tiers and the benefits, as I don't expect much from this going in. I should note this won't affect the videos or the content here either. This is completely optional, as the code will still be visible as we go through the series. Although, if you'd like to say thank you or get access to the tutorial code, or even the latest code as it's merged in, then this will be the place to do it. I won't be overselling this, but for anyone who does take up the offer, it would be much appreciated. Okay, and with that said, let's get back into it. So to quickly review where we were in the last video, we had our fighters fully configured to have their fundamental moves along with looking and acting like their original arcade counterparts, meaning they would now turn around and face their opponent while polishing up any remaining transitional states. We also added our first collision box called a push box, restricting them from ever overlapping. As mentioned, this has put us in a perfect place to extend our state machine and look to add our next set of collision boxes to enable the attacking and hurt states, which funnily enough will do just that in the next video. However, in today's video, I thought we'd take a small break from state machines and tackle the background, scrolling and status bar UI. We'll definitely need some of these in place if we're looking to add our tags anyway. So for our first point of call, let's jump back into our trusted Spriters resource site and pull down 2 more images to help us cater for today's video. As per usual, we'll head into the arcade section, then choose the letter S from the alphabetical list, and then lastly the Street Fighter 2 title from the available games. Once there, we'll first click on the Ken stage icon from the stage section. This image will eventually be used to replace our current background that we've been using since the beginning. You should notice, just like the sprites, all the necessary graphics for the stage have been evenly spaced out across the image. All these parts will eventually make up the final stage background, but we'll discuss that a little later. But now, simply right click on the image and save a copy of it to our project's images folder. I'll be naming it ken-stage.png. Once done, we'll go back to the main page and click on the time over icon in the miscellaneous section. This image contains all the graphics we'll need for the HUD overlay, such as health bars and fonts. So we'll again right click and save the image to the images folder, naming it misc.png. Just to ensure we're all on the same page, you should be able to view both of these new images within VS Code. Notice that we still have our background image file in this folder, which we'll continue to use for the time being. Next, we'll now follow our usual practice and add these new image files to the index.html file using img elements so that they are loaded on page load with the other image files. I'm giving them an alt attribute of stage and misc, respectively. And with those now available, let's go ahead and add our first new entity for a while, the status bar using the new misc image. This entity will present all the information about the current battle at the top of the screen, such as time, health bars, scores and wins. In the Explorer window, we'll create a new folder within the Entities folder called Overlays, and create a new file called statusbar.js. For those that are not aware, you can enter the folder name followed by a slash and then the file name in VS Code, which will automatically create a folder and a file at the same time, which I find to be quite useful when I remember to use it. For reference, this Overlays folder will contain any entities that will draw on the topmost layer of the screen, Nothing to worry about just yet, as we'll explain a little more about layering later in the video. Before moving on, let's quickly have a look at the status bar from the original game that we're trying to build. Let's split it into its various pieces and see what we end up with. It would seem we have 3 sections. The left hand side displays information for the first fighter, while the right hand side displays information for the second fighter. The middle area of the screen, however, seems to contain more general information about the battle itself. For each fighter, we have their health bar, score, number of wins and their name tag. The remainder of the screen has the countdown timer, the high score and lastly the KO icon. So all in all, there's quite a lot of information we'll need to present in this overlay. With this knowledge though, we can look to break down the necessary properties and logic. So within this new file, we'll define a new status bar class along with a constructor as per usual. As this class will need to know certain bits of information about our fighters, we'll pass their reference into the class by adding a fighters parameter to the constructor. Moving on to the local properties, let's first add the image property. And just like before, we'll use a query selector to pull in the image data based on the alt attribute, which we know for this overlay is the MISC file. Next, as we'll know we'll be working with the time counter in this overlay, we'll add a few properties to manage that. Initially the time counter itself, which we know will have a default value of 99, and its delay timer to store the interval as the time counts down. We'll also add a local property to store the fighter's object being passed in. Just like the other entities, we'll now also set up the frames map object to store the necessary sprite details. Again, we'll use the same format as the previous entities, in that we have a string identifier and an array to store the dimensions of the image we'll be drawing from. In regards to the main health bars and the KO icon, rather than drawing it as one whole strip, we'll take these components individually, as we'll be handling them individually too. You'll notice I'm only taking the left health bar here, as we'll be flipping it horizontally, so that it can be used for the right hand side. Meaning we'll take the KO white icon separately too. We'll also need the red version of this icon later, but we'll leave it for now. Next we'll take the full set of number sprites for the time indicator. Notice how they've been named, with their number at the end. This is important as we'll be using this specifically in the drawing of these sprites. And then lastly for now, we'll take both the Ken and Ryu name tags too. Again, notice how I've named them, as we'll be using this in the drawing function too. Moving on to the rest of the class, we'll go ahead and add the necessary update and draw functions just like before, forwarding on the time and context objects. As we'll be drawing a number of sprites to the screen in this class, let's add a helper function that will handle and wrap all of our draw calls. We'll call this helper function drawFrame, and it will take the context, the frame's map object key, and the X and Y positions. It will also take a direction parameter, so that we can possibly flip the sprites, just like we do for the fighters in the fighter class. You'll probably notice the contents of this function we're writing is very similar to the draw function in that class too, in that we have a scale and a set transform wrapping the draw image call. With that function now complete, let's use it within our draw function and start drawing out the status bar UI. We'll first add the health bars and the KO icon using the new drawFrame function. As mentioned, we'll be flipping the health bar for the second fighter, so we'll use a -1 for the direction on that draw call. To see how this looks so far, let's jump back into the Street Fighter game class and add a new instance of the status bar class to the entities array, passing in the fighters as an argument. We'll add it to the end of the list to ensure it draws last and therefore on top of all the other entities. A quick check in the browser and we now have the health bars for both players presented above the fighters at the top of the screen. So far so good. Okay, back in the status bar class, we'll next add the countdown timer. We'll start by taking the time value and casting it as a string. Then using pad start, we'll pad it with zeros to ensure the return string is always 2 characters in length. We'll then use this new time string variable and draw 2 sprites for each number based on the individual characters of that string, using the char@. function. You could use bracket notation here instead if you like, but I find char@ to be a little more declarative. Or maybe I'm just a little too old school. You'll also notice we're using a string literal, prefixing the frame key with a time dash string, and ending it with a character based on the index. This is why it's important to name the frame keys as we did, in the frames map object. Then moving on to the name tags, we'll first deconstruct the name property from each of our fighters, using the fighters array and alias them both into new variables called name1 and name2. Just like the time string we did previously, we'll use a string literal and use the names within the frame key. In theory, this allows us to extend the fighter's rotor, adding more fighter classes, and if they were named correctly, we won't need to update this code as the tags will still match. We are using the toLowerCase string function however, so to ensure we remove any unwanted character casing. Another small check in the browser and it looks like we now have a fully rendered status bar. Okay, let's now get the time to count down and work as it does in the original game. But just before we do though, the main draw function is now looking a little messy at the moment, as I like to break my code down into smaller functions if possible. Let's look to do that here so that it's more obvious what we're actually doing. We'll start by creating a draw health bars function and move the necessary code over to it, remembering we'll need to pass in the context as a parameter. Let's now do exactly the same with the name tags at a time, creating draw name tags and draw time functions. Then we'll just call these functions in sequence within the main draw function. Hopefully you'll agree, this makes our code look more cleaner and easier to read. Following the same pattern, let's create a new function called updateTime, and call this within the main update function, again passing in the time object as an argument. This function will house the countdown logic for the battle time. Similar to how we work with animations, we'll use the time parameter and compare this to the local time property with a set delay period. This means if the delay has now elapsed and is therefore higher than the actual local timer, we'll decrease the time by 1 and then reset the timer in preparation for the next decrement. I found a delay of 664 milliseconds seems to simulate the delay of the original game, as the timer doesn't seem to use actual seconds for some reason. Also, as we don't want the time value to be less than 0, we'll also add a simple check here so that it only decreases the value if it's higher than 0. And with another quick check in the browser, the timer now seems to be counting down as intended, although the original game also seems to make the time sprites flash if the time is lower than 15 seconds, something which currently ours don't do. So let's look to simulate that next. Back in the frames object, we'll add another set of time numbers. These again follow the same naming convention, but have the word flash inserted in the middle for distinction. Next, we're going to add a new constant file that will hold any constants based on the battle, so naturally we'll create a new file in the constants folder and call it battle.js. Continuing to follow our no magic numbers rule, we'll extract the time delay value of 664 for the countdown and add it here with the name time delay. We'll also add 2 more constants that will help us with our time flash sequence. The first one is called time flash delay and will hold a value of 50. Just like the constant before it, this is the length of time in milliseconds the time will display before flipping between the standard set of frames or the flashing set of frames. In regard to the frames themselves, we'll now add a lookup array called time frame keys. Similar to how we've done animation previously, this will hold the frame keys for the flashing animation. Although in this instance, we only need the key prefix, as we'll be using this and combining it with the local time property. Back in the status bar class, we'll import the constants and initially replace the value within the updateTime function with the time delay constant. We'll also update the frames object to use the time frame keys array for both sets of time frames, just to be consistent. This way we're not duplicating strings everywhere. As we want the timer to be able to flash and therefore swap between the 2 different sets of time frames, we'll need a way to update the frame key within the drawTime function. Let's add 2 new local properties called timeFlashTimer and useFlashFrames in the constructor, and set the default values to false and 0 respectively. Then within the updateTime function, we'll add a new condition to see if the time property has a value less than 15 but more than -1. This is the range in which the time should flash. Also, just like before, we'll use the time object to check if the timer has elapsed, but this time use the timeFlashTimer property and the timeFlashDelay constant. If all of these conditions are met, we'll flip the useFlashTimes property and then reset the timeFlashTimer property using the time object. Okay, so now that the useFlashPhrase property will be constantly flipping back and forth between true and false based on the delay, we'll use this to decide the set of frames to draw to the screen. Inside the drawTime function, we'll use this property inside the time frame keys lookup array and return its result to a new variable called flashFrame. We'll wrap it with a number primitive object so that it converts the boolean into either a 1 or a 0, which is perfect for the lookup array. We'll then replace the time string with this new variable inside the literal strings of the drawFrame calls. This means we're now using the correct frame key prefix based on the useFlashFrames boolean, and therefore drawing the correct time frames to the screen. Before we check our work, we'll also add a mathmax around the time property to guard against drawing any values below 0 too, meaning we can now jump back to the updateTime function and remove the time below 0 conditional check from the time delay condition. So again, we'll just quickly check how this looks in the browser, and as you can see, when the timer dips below 15, it now replicates the original game by flashing until it reaches 0. So with the status bar now complete, let's look to move on to the next subject of today's video, the background. Let's open up the stage class. As you can see, it's looking quite barren at the moment, as we've not actually touched this file since the beginning of the series. It's currently just drawing a static background image to the screen that we got initially. Now that we have the actual stage graphics for Ken's background, I think we should change that. We'll start by attempting to replicate the image, but with the individual parts we now have access to from our new stage image. Okay, to do that, let's have a look at what the stage background actually consists of. If you look closely, there is actually only 3 main parts, or layers, to Ken's stage background. The ocean and sky section is actually the furthest layer and the most set back. We then have the boat image, which sits in front of the sky and ocean and floats up and down as if it's sitting on water. And finally we have the floor, which is the closest layer, where it looks a little skewed, but this is on purpose. More on this later. Hopefully you'll notice that these sections, especially the floor, are much wider than those of the original background image we had. This is because, as I'm sure you're aware, the stage scrolls left and right, so those sections had to move with it. Although certain sections or layers move faster or slower depending on how far or close they are to the fighters, giving it a feeling of depth. It should be mentioned that we do have a few sprites that sit on top of the background too. In regards to Ken's stage, these would be bollards, 2 set back near the boat, and a further 2 that appear in front of the fighters. These elements all strengthen the idea of depth on the stage, especially when it's in motion. Let's first change the local image property to point to the new stage image that we downloaded earlier. Next, just like the other classes, we'll create a new frames map object and add 3 entries for the main sections of the stage: the background, the boat and the floor. In the draw function, we'll now draw these new frames to the screen at the same positions to replicate our original background image. Before we can do this however, we'll first have to open up the image in our trusted art tool to convert the pale blue background colour of this image to be transparent instead. For reference, I'm again using graphic scale here. Back in the code, we'll be drawing a number of frames to the screen in this class, so again we'll create a small helper function to wrap the context draw image call. You'll probably realise that we're now replicating this function in a number of classes, so this is a prime target for some refactoring, but as usual we'll leave that till the end of the video. So instead, for now, we'll just copy the draw frame function from the status bar class, and remove the directional property, and remove any unnecessary code as we won't be doing any frame flipping here. With that in place, let's now draw each of these layers to the screen and adjust their X and Y positions so that it replicates the original background. Notice we're drawing these mostly with minus values, and therefore partially off screen. We'll come back to this shortly, but in the meantime, let's see how this looks in the browser. Okay, not bad. If it wasn't for the missing bollards near the boat, I doubt you think anything had changed. But we're now drawing each of these layers individually, which opens the door to allow for motion. This leads us nicely onto the next part of the video, implementing a camera system and scrolling. Although, before we move on, we can safely delete the old background image now as we no longer need it. And before we forget, we'll also remove the reference from the index.html file too. You've served us well, buddy, but it's now time to say goodbye. To make the screen look like it's scrolling, we'll need to think about the coordinate system again that we touched on in the early parts of the series. As we know, all of our entities have a position in the context using X and Y coordinates. Currently, our background layers also work on the same principle, as we're drawing them all based on the origin point of that context. Similar to how we work with origin points on animation frames, to allow for scrolling, we'll need to anchor our entities and background layers to another origin point. In most games, this other origin is called a camera. As we move the origin point or camera, the entities and background will offset that position from their current position, giving the essence of moving around a space in a world. In the case of giving you the feeling of depth, entities will be given a base value, which will be calculated against the camera's position, and therefore its offset, to either speed up or slow down its movement. As you can see here, the sky and ocean layer has a higher base value compared to the floor, so it moves slower and mimics that it's further in the distance. Okay, so back in the code, we'll create a special entity to accommodate this new world origin point. Funnily enough, we'll call the entity camera. So in the Explorer window, we'll create a new file called camera.js in the source folder, alongside our input handler file. In this file, we'll define a camera class, and as per normal, a constructor too. In regards to the parameters, we'll need a starting X and Y position, along with something for the camera to focus on. Naturally, in a Street Fighter game, this will be the fighters, so we'll pass in that object too. We'll next add a position and fighters' local properties and set them up from the constructor's arguments. As this entity is special and doesn't draw anything to the context, it'll only need an update function, so we'll create a stub for that and pass the time and context parameters as per normal. Back in the Street Fighter game class, we'll create a new instance of the camera object and pass in a starting value of 0 for the X and Y positions, along with the fighters array. Now in the update and draw functions, we'll change the parameter list to include the new local camera property. Then in the update function, we'll call the camera's update function separately, as it's not part of the entity array. Jumping over to the stage class, we'll update the draw function to include the camera's argument too. For the draw frame calls, we'll now update the fixed X and Y positions with some known values instead. As we've done previously, we'll wrap any values that could result in a decimal place with a math.floor function to ensure we don't get any anti-aliasing. To explain what we're doing here, all three layers have starting X and Y positions. To anchor these draw calls to the camera, we're deducting its position from these starting positions, just like we did with the animation origin points. You'll notice we're also dividing the camera's position by a base value into some of these layers to simulate depth as mentioned. This is to produce friction on the camera's position so that it slows down the overall speed that it moves. Notice the floor has no base value as it moves in line with the camera's position. The last thing we'll do to test this is to update the camera's start position in the Street Fighter game class. We'll do some magic numbers for now and use an X position of 448 and a Y position of 16. We'll explain what these starting values are in a short while, but let's see how this affects what we have in the browser. And again, after all that, nothing has changed. Not very exciting, I agree, but just to confirm, all the background layers are now actually offset based on the camera's position, which in itself also has a different starting position. To actually see what we've achieved here, we'll implement the same logic we did with the Ken sprite in the first part of the series, by moving the camera's X position and bouncing it back and forth across the stage. So back in the camera class, we'll add a temporary speed local property with a value of 60. Then in the update function, just like the initial part of the series, we'll add this to the camera's X position and multiply by the time.seconds pass value. This should result in roughly moving 1 pixel every 60 seconds. We'll then add some simple temporary logic to ensure it bounces off the furthest sides of the stage. Now in the browser, it's far more clear what we originally set up with the layers. As the camera moves back and forth across the stage, the background layers are adjusting their X position using the camera as its origin point. Also, as mentioned, the base values we use are correctly given the feeling of depth too. The only problem we have now is that the fighters are still excluded from the world, which makes them look like they are sliding. Let's look to update their positions so that they use the camera as their origin point too. Thing is, this is going to be a little more complex. In the fighter class, let's go ahead and bring the camera into the main draw function, and just like before, deduct the camera's position on the draw image call. We'll also need to forward the camera onto the draw debug function, so let's do that too while we're here. Now in that function, let's also adjust the camera's position too where necessary. In fact, it actually seems we're not adjusting for the direction here at the moment either, so let's kill two birds with one stone and add those adjustments too, on both the rect calls. And before we move on, we'll also need to adjust the camera's position on the origin point lines too. As the code is getting a little long here, we'll also create new lines for these changes. Next, we'll move on to the main update function. First adding the camera to this function's parameter list, and then change the update stage constraints call by adding the camera to its parameter list too. Continuing the chain, we'll then go ahead and update the arguments on the actual function itself to match. In this function, we'll first need to update the initial two card checks, again adding the camera's X position to these conditions. You're probably seeing a trend here. This is to ensure the fighters stay within the boundaries of the screen based on the camera's position. Next, we need to update the math min and max functions here to also consider the camera's position. So yet again, we'll add the X position here also to ensure the fighter's collisions also work based on the camera's position. The last thing we'll need to do is update the fighter's starting positions. So back in the Street Fighter game class, we'll change Ryu's X position to 552 and Ken's X position to 728. For those of you who are keeping track, we'll realise that these new values are just the original X positions, but now adds the camera's starting X position to it. Phew! And with that, the initial pass is now complete. If we check the results in the browser, then you'll hopefully notice that both Ken and Ryu are now contained within the view of the camera, and move correctly as if they were in the world space. Even when they hit the edge of the screen, they are still contained and pushed along with the scrolling. Okay, so rather than moving the camera automatically based on a set speed, let's investigate getting the fighters to do this for us as they move around the stage. But before we can do that, I appreciate that we've been using a lot of magic numbers at the moment, so let's look to bring some clarity to this and try to understand the world space dimensions. So time for a little maths session. As we know, the screen size for the game is 384 pixels wide by 224 pixels tall. In comparison, Ken's stage is 768 pixels wide by 256 pixels tall. We know the camera is usually positioned in the middle of the stage at the beginning of the battle. So to work out what the starting position is, we'll take the stage's width of 768 and divide it by 2, which equals 384. This makes the stage 2 screens wide. We'll also need to divide the screen by 2, which equals 192. So 384 minus 192 is itself 192. So far so good. However, one thing we've not taken into account is the floor. If you were to measure the width of the floor frame, you'll notice it's actually larger than the stage width, at 1024 pixels. The reason for this is to cater for the 3D effect and the way it skews the image. We'll come back to this later, but for now, if we minus the width of the floor with the width of the stage, we get a value of 256. This is the padding we'll need to apply to the starting position. So 384 minus 192 plus 256 equals 448. So this makes the starting position of the camera 448. From this information, we can generally work out any of the other X positions for the moving entities on screen. For example, the fighters are 88 pixels on each side of this midpoint at the start of the battle, which ultimately works out at 552 for Ryu and 728 for Ken. In regards to the Y position, this is incredibly simple in comparison. The stage height has a buffer of 16 pixels at the top and the bottom of the actual screen size, although usually it's only the top 16 pixels that are used, for example when the fighters jump. The bottom 16 pixels are just used for overflow and are therefore usually not visible or used. And there you have it, math lesson's over, and hopefully the stage boundaries are now less clouded in mystery. With this knowledge, let's now move our magic numbers in our code over to the stage constant file so that we can reuse them. At the moment we only have the stage floor const variable that has a value of 200. Thing is, we know that the camera has a 16 pixel buffer at the top of the screen, so let's add this to this value to make it 216. We'll then add a stage width const, which we know has a value of 768. And just for ease, we'll add a stage midpoint const too, that we'll use to divide the stage width value by 2. And lastly, we'll add the known padding value of 256 and set it to a stage padding const. Before we move on, we're still missing one more value, a const value for the fighter's distance from the midpoint. So in the fighter's constant file, we'll add a new const called fighter start distance and give this a value of 88. Now, within the Street Fighter game class, we'll update both the fighter and camera's start positions to use these new values, replicating the calculated values we had earlier. Also, one thing we've forgotten to update is the fighter's shadow. So let's jump back into the shadow class and repeat the same process there as we did with the other entities, adding the camera to the draw call parameters and then subtracting its position from the drawn image X and Y position. Checking the browser now and things work just as they were before, but the fighters are repositioned on the stage floor and they have their shadows back. Okay, let's get to work on making the camera scroll properly based on the fighter's position rather than bouncing back and forth. In the fighter class, we'll now remove the auto scrolling code as we no longer need it for this. Instead, we'll tackle the vertical scrolling first, because as mentioned, this is far easier to solve than the horizontal scrolling challenge we have in front of us. In fact, you may be surprised to hear that it's a simple one-liner. As we know, we have 16 pixels vertical buffer at the top of the screen to play with, and as the camera needs to keep the focus on the fighters, we'll get both of the fighters' Y positions and find which one has the smallest value, using the math min function. We'll then divide this value by 10, which is its base value, and then wrap this in a math floor function to remove any decimal places. Finally, we'll use a -6 as a starting value to complete the 16 pixels overall. We'll set the result to the camera's Y position, meaning it'll always keep the fighters in focus while adjusting correctly within its buffer. You can see evidence of this from within the browser when the fighters jump. Notice how we correctly adjust the camera based on the fighter with the lowest Y position, and is therefore closest to the top of the screen. Moving on to horizontal scrolling, this is a little more involved, so let's bring up our little diagram again. Unlike vertical scrolling, we have to cater for a number of things, mainly how the camera keeps its focus on the fighters, and how it stops them from pushing the camera out of bounds. The viewable section of the camera is actually split into 3 sections, the middle area and 2 sections on each side of it. These sections are 100 pixels in size and are used to trigger the scrolling. This means the middle section results in having the remaining 184 pixels. In regards to how these are used, if both fighters are contained within the middle area, the camera will be stationary and will ignore their movement. If one of them moves into these sections, while the other is in the middle section, the camera will move based on their velocity, pushing it in that direction. Although, if a fighter resides in both of these sections, the camera will divide the available space between them, attempting to keep the focus on both fighters. Either way, if a fighter touches the furthest edges of the screen, the camera will become stationary again, blocking any further movement in the opposite direction. So as you can see, there's quite a few scenarios we need to solve here. So to start us off, we'll add a new constant to the stage constant file, called scroll boundary, and set this to our known value of 100. While we're here, we'll also add a stage height constant too, which we know has a value of 256. Returning back to the camera class, The first thing we'll need to find is which of the fighters has the lowest and which has the highest X position. We'll do this by wrapping a min and max function around each of them and holding the return values in a low X and a high X variable. We'll then check the distance between these two values and decide if the fighters are within the 100 pixel boundaries on each side of the screen. Depending where the fighters are, we'll drop into two separate branches of logic. If they are within the boundaries, we want the camera to find the midpoint between both fighters and center the screen on that position. So we'll first find the middle value by subtracting the low value from the high value and then dividing it by 2. We'll then use this midpoint value and set the camera's X position to it. We'll then need to add the lowest value back as the base, and then subtract half of the canvas's width to ensure we bring it back to the available screen's width midpoint. We'll next loop over the fighters and check to see if either of them are overlapping either of the scroll boundaries and that they are actually moving. If so, we'll add their X velocity to the camera's X position, pushing it in the right direction, not forgetting to use the fighter's direction and time object to ensure we're using the correct value and time delta. Lastly, we'll add an X and Y upper and lower limit checks to ensure the camera does not go out of the stage boundaries, using the stage constants and the context sizing values for the limits. As we know the fighters are unable to leave the camera area, this will keep the fighters restrained within the stage bounds too. It's wise to check VS Code has not incorrectly formatted the import here, like it has for me. If it has, quickly fix that before moving on. Checking the results in the browser now, the camera should correctly follow the fighters around the stage. When the fighters are in both of the scroll boundaries, the camera will attempt to keep the available space between them in the middle of the screen. Likewise, if only one of the fighters are within a scroll boundary, the camera will be pushed along at the same speed as the fighter's X velocity. And looking at the time, I think that's where we'll leave it today. Unfortunately, there's still a number of things we're missing in regards to the background on the overlays, so we'll roll these over to the next video. But as per usual, there's a number of things I'd like to refactor before we close today's video. One of those changes I like to perform relates to extracting the draw frame call we have in a number of entity classes. So we'll start by adding a new utility module called context.js, adding it to the util folder fully enough. From here, we'll go to the status bar class and copy the draw frame function from there and paste it into the new context module. As this function is no longer a class, we'll obviously need to export it too. We'll update the parameters to include the image reference, as we no longer have one. Same with the frame key parameter, as we no longer have the frames object either, so we'll change these over to use the dimensions instead. Back in the status bar class, we'll now update the contents of this function to call our new draw frame function from the context module instead, passing on the image and frame key dimensions as required. Let's now also go to the stage class to do the same here. Updating the contents of the draw frame call, migrating it over to the context module version. We can't use this new function for either the shadow or the fighter entity just yet however, due to the extra features they need, but we'll look to cater for those in a later video when we talk about more advanced refactoring. The next refactor will be for the name we're drawing within the status bar class. As the names don't change once the battle has started, we'll move this logic into the constructor for a little optimization. We'll first move the name deconstruction line from the update names tag function and create a new local property that does the string interpolation here instead, so that it's a one-time thing as the class is initialized. We'll now use the new names property within the draw names tags function, replacing the frame keys within the draw frame call. Next up is the constructors for the Ken, Ryu and fighter classes, simplifying them somewhat, now that we know more than we did initially. To be honest, the only thing we need to know from the fighter's point of view is its ID. Everything else can be calculated from that. So let's remove everything from the arguments and move the rest to the fighter class. We'll start by fixing the Ken and Ryu classes to mirror what we've just done to the Street Fighter game class, forwarding on just the name and the ID. Then in the fighter class, we'll do the same here too. Within its constructor, we'll then update the position property to use the stage floor constant. For the direction, we'll change this to a ternary and set its value based on the ID. In the same vein, we'll then update the X position now too, to set its value based on the ID too, using the formula we had before in the stage constants. We'll this time however use the ID to determine the distance from the middle of the screen. The last change we'll make today is to move the getContext function over from the Street Fighter game class to the new context module, as that seems to be the most obvious place to put it now. Once moved, we'll update the reference where it came from. We'll also tidy up any unused import references while we're here. Another small check and test within the browser, just to ensure we haven't broken anything, and thankfully, that doesn't seem to be the case. The fighters are still positioned correctly at the start of the battle, and everything seems to be drawing to the context area as intended. Okay, and with that, let's stop there and review what we've completed today. Continuing the sentiments from the last video, we're making good progress with the current code updates in replicating the original game. Being able to scroll the stage back and forth based on the fighter's movement, which in itself has the parallax effect, really does set the scene. Also, having the health bars at the top of the screen just reinforces where we're going next too. As per usual though, I had planned to put a lot more into this video, but time really got away from me on this one. In respect to the background, we're still missing the animated characters and the skew effect on the floor. Also, we're missing the scores and the win icons and the status bar, but we'll come back to these soon, possibly in the next video. I'm undecided if I want to complete those or introduce attacking moves. It'll be a surprise I guess, unless there's an option you prefer. Why not drop your suggestion in the comments section below, to try and persuade me one way or the other. Actually, on a separate note, I'm finding these videos are taking longer to complete than normal at the moment, now that we're starting to explore more complex topics. So unfortunately this is the reason for the lateness of this video, so the release schedule might be a little erratic as we continue, especially as I'm attempting to finish the code as we go. We'll see how that pans out, but if possible, please keep up to date with the vlogs, as I'll drop the latest news there if you're interested. I'll attempt to get the next part out a little quicker before I go on a month hiatus in September for my summer vacation, so expect that to drop sometime early in October. And finally, thanks again to all the support so far, it's really appreciated. Again, if you've got this far, a special acknowledgement goes out to you too, as I find that's a rarity in these videos. So with that, I'll say my goodbyes and hopefully I'll see you in the next one. Ant out.